What's up, everyone? All right, for this lesson, we're going to dive into what we call advanced trigonometric identities. So we've already learned all the possible identities for this unit, but we're going to add a few more, and then we're going to really apply all these different identities into various concepts that you're about to see. So first off, if you haven't already, I would definitely recommend taking a minute or two, or however long you need, and fill out the entire top section of the trig identities, because you've got to know these like the back of your hand. So just to kind of add in, I did include 9 blanks because you also want to do the variations. You need to know every variation of all the Pythagorean identities. And then down here for the double angle identities, I also took a minute, and you need to also include the variations for double angle cosine. So take a minute, fill in all the possible identities you can, and then just do a brain dump, see what all you know or don't know. So I already wrote them in, I just wrote them in white. So I can do this, so you can check. Whoops, my parenthesis, come back. There we go. So definitely take a minute, check every possible identity, make sure the signs are right, make sure the trig ratios are right, make sure every single detail matches exactly what I have. With that, let's go ahead and get started. So we're just going to kind of dive right in. Down here, we're going to solve all the following equations over the interval from 0 to 2 pi, but I'm also going to do all possible. I may not do all possible on some of these just to kind of save some time because this video is probably going to be pretty long. So another thing I want to point out is you probably also see the half angle identities that I have written over here. I went ahead and just typed them out for you because the first time you see them, I don't want you to have to write them down wrong and potentially learn them wrong. So I just went ahead and typed them out for you. We're going to dive deep into these in a little bit, but not right now. We're just going to kind of do some solving. And then as you can see, then we have a whole page and section for half angle. So we'll get into that a bit. So diving right in. So we're going to solve cosine x plus 1 equals sine x. And we want to find the values from 0 to 2 pi and all possible. Now, just know that on any assessment, you will be expected to read the directions so that you know which of these scenarios that you're going to be expected to write. So typically, we only ask for one or the other. We don't ask for both. But on the notes and the video, just so you can kind of get an idea of what they both look like, I try to do both on the notes. But just know that on any assessment, we're only going to expect one or the other, typically not both. So for this first problem, we don't really have any identities here, so nothing is squared, so I can't do any identities like that, so I can't do Big Papa. However, what you can do to create identities is I'm actually going to start by squaring both sides. So that's really what's going to be able to give us something to work with. So notice how because I'm squaring both sides already right off the bat, that does mean we're going to have to check the solutions. So we're going to have to check for extraneous. So remember, the only time you have to check solutions is when you either square both sides and or when you multiply both sides by a trig function. So in this case, our first step, we're already going to have to check. So I'm going to go ahead and multiply this out. So when I multiply it out, we're going to get cosine squared x plus 2 cosine x plus 1, and then that's going to equal sine squared x. Now, in this case, if you look at your trig function so far, I have 2 cosine values and then I have a sine value. So you definitely want to change your sine squared value in terms of cosine. That way we can just work with 1. So I'm going to change my sine squared x. So I'm going to have cosine squared x plus 2 cosine x plus 1. I'm leaving the entire left side alone. But sine squared x I'm going to replace with 1 minus cosine squared x, which is part of your identities. And then I'm going to move everything to the left side, so I'm going to subtract 1 on both sides so that the 1s are gone, and then I'm going to add a cosine squared x on both sides. Sorry if my handwriting's kind of terrible. Wow, and lopsided. We're doing amazing. So this is going to give me, 2 cosine squared x plus 2 cosine x, and that's going to give me 0. When you get to this point, now you're going to look for a greatest common factor. So if you look at both of your individual terms here, they both have a 2 cosine x, so that's what I'm going to factor out. So 2 cosine x, and then when I take that out, what that leaves me with is going to be cosine x plus 1, and then set that equal to 0. And when you get to this point, when you have clearly defined in separate terms, when you get here, then you're going to split or separate, and then I'm going to set each of these terms, I'm going to set them equal to 0 and solve. So on the left side, I'm going to take my 2 cosine x and set that equal to 0. So I'm going to divide both sides by 2. So that leaves me with cosine x is equal to 0. So when cosine is equal to 0, well, that's going to happen straight up and straight down on the unit circle, which means that's going to happen at pi over 2 and 3 pi over 2. So we have 2 solutions so far, which we are going to have to check. And then over here, I'm going to do cosine x plus 1, set that equal to 0, which means we're going to have when cosine of x is equal to -1. Now that only happens in one place on the unit circle, and that is directly far left, so horizontally far left. And that radian is going to happen at pi. So we have 3 solutions that we're going to have to check. So we may have extraneous, we may not. So when you check, I'm going to take all 3 of my solutions over here, and I'm going to plug them into the original. So when you check, you're going to plug in your solutions one at a time. So I'm going to do pi over 2 first. It doesn't matter which one you do first. So cosine pi over 2, and then plus 1. And then I want that to equal sine of pi over 2. So in order for the solution to work, it has to yield a true statement. So we'll see what that looks like, hopefully. So cosine of pi over 2 is going to give me 0 plus 1 equals sine of pi over 2, which is 1. 0 plus 1 equals 1. That is a true statement, which means pi over 2 is going to be a solution. So now I want to do the same thing, but for 3 pi over 2. So cosine 3 pi over 2, that is a 3. Close enough. Plus 1, and we want to see if that's going to equal sine of 3 pi over 2. Now, cosine 3 pi over 2 is 0 plus 1, and then sine of 3 pi over 2 is -1. So 0 plus 1 does not equal -1. So that is a false statement, so 3 pi over 2 would be considered extraneous. And then we still need to check pi. So cosine of pi plus 1 equals sine of pi over 2. Not pi over 2, hello. Sine of pi. So cosine of pi is going to give me -1 plus 1 equals sine of pi, which is 0. So -1 plus 1 equals 0. That is a true statement, which means pi is going to work. So your solutions, we are only going to want pi over 2 and pi. Now, nothing is across from each other on the unit circle, so if I were to do all possible, so it would be pi over 2 plus 2 pi k, and x equals pi plus 2 pi k, where k is an element of those integers for both. Wow, my handwriting is actually terrible today. I mean, it is every day. Ta-da! Number 2. So with number 2, now, as you can see, we have 2 cosine x plus sine of 2x. So now we're going to start throwing in some double angles. Yay. So I'm going to start rewriting the sine of 2x in terms of sine and cosine. So I'm going to leave the 2 cosine x alone. And then I'm going to rewrite sine of 2x using an identity as 2 sine x cosine x. So that's your double angle. Ooh, hello. That's your double angle identity from above. So when you get to this point, now I have 2 cosine x plus 2 sine x cosine x. You want to look in both. You want to look in. I don't know what that was. You want to look in both terms. Come back. Oh, you want to look in both terms and see what they both have. So I can see that we have a 2 cosine x and a 2 cosine x. So I'm going to factor out a 2 cosine x. And when that happens, I'm going to be left with 1 plus sine x. And that's going to equal 0. So same idea here. You're going to split and solve. So we're going to have 2 cosine x equals 0. divide both sides by 2, which means we're just going to have cosine x equals 0. And then that's going to happen at pi over 2 and 3 pi over 2, just like before. That was not on purpose. That was on accident. Whoops. Did not mean to use the same type of equation. And then over here, we're going to have 1 plus sine x. And that's going to equal 0. So this is going to be when sine of x is equal to -1, which is only going to happen at 3 pi over 2. So we have only 2 solutions because we have a repeat. So in this case, for your solutions, we're just going to have pi over 2 and 3 pi over 2. So you would not write the 3 pi over 2 twice. You're just going to write it once. Now, in terms of all possible, the pi over 2 and 3 pi over 2 are across from each other. So we can write it as a single equation plus pi k instead of 2 pi k, where k is an element of those integers. Ta-da. Moving on. Number 3. So with number 3, as you can hopefully see, if you look over here on the right side, you see this absolute blasphemy. So this is 2 cosine squared of x divided by 2, or 1/2 x. Now with that, that is going to be one of the new identities that we're going to use. So we're just going to reference it for this problem, but I'm going to do a deep dive in half angle in a little bit. So we're looking at cosine. So whenever you see a half angle for cosine, we're going to do the square root of 1, that's not a plus. We're going to do 1 plus cosine x all divided by 2, and then we're going to take the square root of it. So it looks a lot worse than it actually is. Half angles actually aren't terrible. So I'm going to rewrite everything in terms of just cosine x. So I'm going to have 1 plus cosine squared x. I'm going to leave it alone. And then we're going to have 2 times the half angle identity. So the half angle identity for cosine is going to be 1 plus cosine x, and then divide by 2. And then we're also squaring it, which means I'm going to square this. And then I also need to move this down because what am I doing? So now I'm going to simplify it. So I have a square root, and I'm also squaring it. So those 2 operations are going to simplify since those are inverse operations. So I'm going to have 1 plus cosine squared x equals 2 parentheses 1 plus cosine x all divided by 2. And then notice how I'm multiplying by 2 and then I'm dividing by 2. So then those values are going to simplify as well. So we're going to have 1 plus cosine squared x equals 1 plus cosine x. And then I'm going to move everything to the left side so I can start solving and evaluating. So I'm going to subtract 1 on both sides. So those 1s are going to be gone. And then I'm going to subtract cosine on both sides. So what's going to happen is we're going to have just cosine squared x minus cosine, and that's going to equal 0. Now, once again, you're going to look for a greatest common factor. So I can factor out a cosine x. And then that's going to leave me with cosine x minus 1. And that's going to equal 0. So now you're going to split and solve. So over on the left side, I'm going to do cosine x equals 0 again. So that's going to be at pi over 2 and 3 pi over 2. Apparently, I love those values. And then over here on the right side, then we're going to also do cosine x minus 1 equals 0. So when cosine x is equal to positive 1, which means that's going to happen at 0. Now, in terms of checking solutions, which I forgot to mention this on number 2, so I'm going to go back to number 2 for a split second. Now on number 2, notice how I didn't check my solutions. I just boxed them and moved on. We did not square both sides at any point, and we did not multiply both sides by a trig ratio at any point. So I don't need to check my solutions on number 2. We're not going to have any extraneous solutions. Now, same idea over here on number 3. We did not square both sides. We did have this value here that was squared, but it wasn't an operation to both sides. It wasn't sort of simplifying per se. So I don't need to check my solutions on this one either, since I didn't square both sides and I didn't multiply by a trig ratio. So keep that in mind. Which means for my final answer over here, I'm going to have solutions at 0, pi over 2, and 3 pi over 2. In terms of all possible, so I don't have any other solutions other than 0, So pi is not also a solution, which means I have to do a full period of 2 pi. So for all possible, this would be x equals 0 plus 2 pi k, which this can just be rewritten as 2 pi k. I don't need to write the 0. And then k would be an element of the integers. So I want this equation. I don't need that equation. And then for the pi over 2 and 3 pi over 2, once again, as we've done before, that's just pi over 2 plus pi k, not 2 pi k, just pi k, since those are across from each other on the unit circle. So I would just need these two equations if I'm doing all possible. Let's move that up. Okie dokie, I'm gonna make sure I'm doing the right ones. So I'm only going to do certain ones. So 4 and 6 are really similar to problems that we've either done prior or before this video or something else. So I'm going to skip those for sake of time. So we're going to jump to number 5. So with number 5, we have 4 sine x cosine x equals -1. So I can look at this equation and I can see, oh, this looks oddly similar to 2 sine x cosine x. The only difference is we need a 2. And over here we have a 4. So to me, this is an indicator that I'm going to use a double angle identity. So I need to I'm going to manipulate that equation to look like this for my double angle sign. So I need this coefficient in the front to actually be a 2 in order to use that identity. So what I'm going to do is I am actually going to divide both sides by 2. So I can use the identity. Which I know typically we see this when we want to divide by 4, but if I divide by 4, I still don't have any identities that I can use, so dividing by 2 is going to be your best bet. So that's going to leave me with 2 sine x cosine x, and that's going to equal -1/2. And now that I have an identity on the left side, I'm going to rewrite this as sine of 2x equals -1/2. Now for the next part is we're going to kind of ignore this 2 for a second, and I just want to evaluate sine of x when it's equal to -1/2, and then we're going to bring in that 2 in the next couple steps. So sine of x equals -1/2, that's going to happen at 7 pi over 6 and 11 pi over 6. So once you evaluate for just that specific value, now I'm going to bring in that 2 back. So now I'm going to have 2x, and I'm going to set it equal to those exact solutions that we just did. So in order to solve for the x value, what I'm going to do is now I'm going to multiply all the solutions by 1/2, or divide everything by 2. So with that, that means our solutions are actually going to be 7 pi over 12 and 11 pi over 12. So we have these two solutions. Now, I want you to kind of pause for a second. I'm going to re-emphasize another point in our directions. We're looking for all the solutions from 0 to 2 pi. If I think about where 7 pi over 12 and 11 pi over 12 are on the unit circle, that's going to be only in quadrant 2. So like 7 pi over 12 would be right up here, and then 11 pi over 12 would be about over here. So that's not all the values. So what you need to do next is you need to consider the period of your actual equation. So when I say period, I'm going to reference back up here when I used a double angle identity. So I'm going to kind of recap. So the period of your trig function is equal to 2 pi divided by your b value, back when we were graphing trig functions. So this is going to be equal to 2 pi divided by our b value, which if we reference this equation, it's going to be 2. So when I simplify, we're going to do 2 pi divided by 2, which is only going to give me pi. So your solutions, we actually have to consider the multiples or the period values of 7 pi over 12 and 11 pi over 12. So meaning, even though my domain goes from 0 to 2 pi, if I rewrite this in terms of a denominator of 12, that means we're actually going to look from 0 to 2 pi, which would be the same as 24 pi over 12. So I know you're probably thinking, what is he actually doing right now? So what I'm going to do is I'm going to take each of my solutions. So 7 pi over 12, and then I'm also going to take 11 pi over 12. And we need to actually add the period to both of these until we get up to 24 pi over 12, because we're going to have potentially more solutions than just these two because of the period. So what I'm going to do is now this is going to change into 7 pi over 12 plus 12 pi over 12, which means I'm going to also have 19 pi over 12 as a solution, because that is within the interval. So I know I'm going to have 7 pi over 12, and I know I'm going to have 19 pi over 12. So now the next part I'm going to do is going to be down below. Or actually here, let's go back up here. So let's say I decide to try to keep going. Let's say I try to add another pi. So if I do that, that's going to give me 31 pi over 12. Well, 31 pi over 12 is not going to be in the interval, so I would not include the 31 pi over 12. So this is how you know when you're going to stop. So same idea down here. So we have 11 pi over 12 plus pi. So this is going to be 11 pi over 12. And then we're going to add another pi for the period. Yes. Sorry, my brain stopped working for a second, y'all. So 11 pi over 12 plus 12 pi over 12, that's going to give you 23 pi over 12. Ooh, that one's cutting it close. So this one's right before the cutoff, and I cannot draw a check mark. There we go. So that one is slightly less than 24 pi over 12, so we can also include that one. So we're actually going to have 4 solutions. So we're going to have the 7 pi over 12, 19 pi over 12, 11 pi over 12, and 23 pi over 12. So in this case, if I'm doing just the single cycle solutions, that means I'm going to have 7 pi over 12. Then I'm going to do 11 pi over 12. I'm going to put these in order. And then we're going to have 19 pi over 12. And then we're going to have 23 pi over 12. So in a single cycle, these would be all your solutions. Now, if I want all possible, then that means I would want the 7 pi over 12 plus pi k, which is our period. And then we're also going to want the 11 pi over 12 plus pi k, where k is an element of those integers. So there's single cycle versus all possible. I know this one was kind of tricky because of the period, but it's actually a really good problem, y'all. Like, this is a pretty solid AP level question. So speaking of pretty solid AP level question, number 7. So now, instead of doing a double angle, now we're actually looking at a triple angle. So yes, it does go past just double angle, triple angle. Like, you could have any angle you want. You could have a quadruple angle if you really want. So with this one, so it's going to follow the same mechanics and schematics as number 5. So with this one, you're still going to solve it. I'm going to add, whoops, that was not a good idea to do. I'm going to add the root 3, and then I'm going to divide by 2 on both sides. So I'm going to skip kind of those algebraic steps. So I'm just going to go directly to cosine of 3x is going to equal to root 3 over 2. And then same idea, I'm going to ignore this 3 for a second, and I just want to evaluate when cosine of x is going to be equal to root 3 over 2. So that's going to happen at pi over 6 and 11 pi over 6. So once we have this, now I am going to have to plug that 3 back in, and now I want 3 times that value is equal to pi over 6 and 11 pi over 6. So when I divide everything by 3 or multiply everything by a third, whichever you want to do, it's all the same, that's a 3. So either way, so when you get here, then you're going to get pi over 18 and 11 pi over 18. Now, same idea up here. These values, let me fix this. This is going to bother me. Pi over 18 and 11 pi over 18. A little bit better. So same ideas up here. We also need to account for the period. So down here, for the period. So this is going to be 2 pi divided by your b value, which in this case is going to be 3. So our period that we're going to have to add is going to be 2 pi over 3. So over here, we have a denominator of 18. So when I'm adding 2 pi over 3, I'm going to convert this to a denominator of 18. So if I want a denominator of 18, well, that's times 6. So I'm going to multiply the top times 6, which means this is going to be 12 pi over 18. So that's what I'm going to add to my solutions so long as I'm within the interval. So if I'm over a denominator value of 18, my domain, so personally this helps for me, but you don't have to do this part. So for me, I like to visualize what the new domain is going to be. So if I have a denominator of 18, that means I can go up to 36 pi over 18, which is still 2 pi. So when I do this part over here where I'm looking for more solutions using the period, I know the numerator value cannot exceed 36. So that's how I know when to stop. So I'm going to take my two solutions. So pi over 18, which is going to be my first solution. And then I'm going to add the period, which is 2 pi over 3. So I'm adding the period, which is 2 pi over 3, but I'm going to go ahead and just convert it to a denominator of 18. So I'm going to go ahead and just add 12 pi over 18. So when I do this, then we're going to get 13 pi over 18. And then I'm going to add another period. I'm going to keep adding that period until I max out that numerator. So when I do that, then that's going to give me 25 pi over 18. And then if I add again, so then we're going to have 37 pi over 18, which that's exceeded the numerator, so we can't have that one. But from this first set, we can have pi over 18, 13 pi over 18, and 25 pi over 18. So we've got 3 solutions total so far. Well, actually 4 if we count for the first solution of the next set, which is 11 pi over 18. So same idea, I'm going to add the period, which is going to be 2 pi over 18. So when I do that, so 12 pi over 18, there we go. So when I add here, so that's going to give us 23 pi over 18. Let's see if I can do some basic math here. Basic math is hard, y'all. Then I'm going to do another 12 pi over 18. So when I add here, that's going to give me 35 pi over 18. And that's right on the cusp of the 36, so I'm going to go ahead and just stop there. So I know I have 11 pi over 18, 23 pi over 18, and 35 pi over 18. Ooh, lordy, this is a good one. So that means individually, if I'm looking at a single cycle, we're going to have pi over 18, 11 pi over 18, 13 pi over 18, 23 pi over 18, 25 pi over 18, and 35 pi over 18. So that would be our single cycle. Now if I want to write all possible, so I'm only going to use the first 2, and then we're going to add the period. So for all possible, we're looking at pi over 18 plus the period times k, which would be 2 pi over 3k, where k is an element of those integers. And then same idea down here. Then this would be x is equal to 11 pi over 18 plus the period times k, which is going to be 2 pi over 3k, where k is an element of these integers. So this would be your all possible solutions for this one. So I'm just saying, I love this problem. It's a great problem. Okie dokie. So with 18, not 18, hello, I don't know math. I don't know numbers, it's fine. With 8, 9, and 10, I should have been way more specific in the directions, which I wasn't, so that's my own fault. But for these, we're only going to rewrite. So that is what we're going to do on 8, 9, and 10. So that is my own fault for not being a little bit more clear on these. I'll just do it right there. And over here. So on these three problems, we're just simply rewriting the equation. We're not solving. So if you look at number 8, not 18. That's why I was looking at 18. So when we look at number 8, so we're given the equation 18 sine of 8x cosine 8x. Now this looks very similar in terms of formatting to a double angle for sine. So what's going to happen is I need to change my equation and manipulate it a little bit so that I can use an identity. It's going to be a similar schematic to what I did up here. So I changed it to look like the 2 sine x cosine x so that I could change it into a double angle. So we're going to do the same idea here. So the coefficient needs to be a 2 in order for me to use that double angle. So that means I'm essentially going to divide this number by 2, and I'm going to rewrite it. So I'm going to do 9 times 2, and then we're still going to have sine of 8x, cosine 8x. And then what I'm going to do is I'm going to rewrite just this part as a double angle. So I'm going to leave that 9 out in the front, and then we're going to have sine of 2 times that angle in question, which in this case is going to be 8x. So then you're going to rewrite it as 9 sine of 16x, and that would be how you rewrite. So that's all that's going to be expected on these types of questions when you're rewriting. You're going to be looking for equivalent forms. Now down here for number 9, once again, we're just going to rewrite. Now if you look at the setup and the format of this type of question, if you look on the left side, we have sine of x plus pi over 4, which means we're going to add 2 separate angle values together. So when I'm adding 2 separate angle values using sine, what that tells me is this is going to be a sine summation. Now, when I say a sine summation, that means we're going to use sum and difference identities. So your sum and difference identities, we're going to be using these equations over here. So we're going to follow this type of format. Now, remember with sine, if we're adding in the equation, we're still going to add in the actual formula. But remember with cosine, cosine's kind of your booger. If I'm adding in the formula, we're actually going to subtract in the equation. And vice versa. If I'm doing a minus b, then we're going to add in the formula. And then you can kind of take a peek at tangent. Notice how we have both a plus minus and we have a minus plus. So just be cognizant of those signs because those signs really do matter. And they really can make or break your entire problem. So getting started on this one. So I know I'm going to have an a value of x and a b value of pi over 4. So my setup for a sine summation is going to be sine of a, cosine of b, plus cosine of my a value, and then sine of my b value. And then for this problem specifically, I'm going to set that equal to 1/2 because of what we have over here. So now I'm going to plug in. So this is going to turn into sine of x, then cosine of your b value, which is pi over 4. And then we're going to add cosine of your a value, which is x, and then sine of my b value, which is pi over 4. And we're going to set that equal to 1/2. So now what you're going to do is you're going to evaluate, I guess evaluate would be the right word. So you're going to evaluate those sine and cosine of pi over 4 values. So sine of x, you don't know what that radian is, so you're just going to leave it alone. Cosine of pi over 4, I know that that would be root 2 over 2 from your unit circle. And then we're going to have plus cosine of x, and then I know that sine of pi over 4 is going to be root 2 over 2. So I can evaluate that as well, and then we're going to set that equal to 1/2. Now when you get here, technically, yes, it's rewritten. Technically, yes, it's been simplified. However, there's various forms in which you could be expected to write these in. So if you look, we also have denominator values of 2 across the board. So whenever that happens, what we typically like to do is get rid of these fractions. So I'm going to multiply everything by 2. So doing that means we're going to have sine of x times root 2, then plus cosine of x times root 2, and then that's going to equal 1. And then from here, what we like to do, we're going to take these values over here, the root 2's, and we're going to turn these into coefficients. We want to write those in the front. So, I mean, it's not mathematically any different if you leave them in the back, but we just like to write them as coefficients. So root 2 sine of x plus root 2 cosine of x is going to equal 1. Now, this is one way you could write it. Addition is commutative, so the order doesn't matter. So you could also rewrite it as root 2 cosine x plus root 2 sine x equals 1. And that's the same exact thing. Now, over here, so typically I would just skip this one because it's really similar, but I actually want to do this one to show you what happens with this negative. So with cosine, so it's the same idea. So we're doing cosine difference. So we have our a value and our b value. So I'm doing cosine x minus 2 pi over 3. So my equation here that I'm going to do is going to be cosine a, cosine b, and then I'm going to change the sign. It's going to be opposite of what you see for cosine. And then sine a, sine b. And then that's going to equal negative 1/2. So once again, I'm going to approach this problem just as I normally would. So we're going to have cosine of my a value, which is x, cosine of my b value, which is 2 pi over 3, and then plus sine of x, and then sine of 2 pi over 3. And then once again, set that equal to negative 1/2. So now I'm going to evaluate the cosine 2 pi over 3 and the sine 2 pi over 3. So I'm going to rewrite those using the actual values. So this is going to be cosine of x. Cosine of 2 pi over 3 is negative 1/2. So don't forget your positives and negatives. And then sine of x, and then sine of 2 pi over 3 is going to be positive root 3 over 2. And then that's going to be equal to negative 1/2. Now, once again, if you look, we have denominator values of 2 across the board. So I'm going to multiply everything by 2. Now, when you get here, this is where you have technically options. Technically, I could multiply both sides by either a positive 2, or I could multiply both sides by a negative 2. So it just depends on if it's multiple choice, if it's free response. You may be expected to multiply by a positive or a negative depending on the possible answer choices if it's multiple choice. So who knows? If it's free response, we'll take either one technically. So I'm going to show you both. So the first one I'm going to do, actually, let's do this. So I'm going to do option 1 over here, and I'm going to do option 2 over here. That way you can see both. And you can see all the variations. So over here on the left side, let's start with a positive 2. So if I were to multiply by a positive 2, that means I'm going to have a negative cosine x. Go away. No, not Schoology. Go away. So negative cosine x, and then plus sine x times root 3, and then that's going to equal a negative 1. Now, typically when we write equations, we don't typically like to start with a negative. So what mathematicians like to do, whoops, let me write the coefficient. So typically we'll write it as root 3 sine x, and then minus cosine x equals negative 1, just because we don't like to start with a negative, but either way, this would be accepted and this would be accepted if it was free response. Now over here, let's multiply by a negative 2, kind of see how this changes up. So with this, if I multiply by a negative 2, so then this would be positive cosine x minus root 3 sine x equals a positive 1, so that could be a variation. Or if we like to go the more unorthodox route, we could do negative root 3 sine x plus cosine x, and that equals 1. So once again, either of these variations, if it's free response, any of these 4 would be accepted, but just know that if it does happen to be a multiple choice question on, say, like the AP test, you know that there are different variations and ways of writing the same equation. All these would be equivalent. Okay, so personally, I would say if you're still here, I would definitely take a break here if you can. Before we do half angle, because we're about to transition to the next thing. So this would be a good kind of place to kind of take a break. But anyways, I'm going to keep going. So now we're going to transition into half-angle identities. So with half-angle identities, I have the identities written on the front, but I'm going to write them down on the back page down there so I don't have to keep scrolling back and forth. So with half-angle, it works very similar to double angle. Well, if I have a radian value and I'm going to double it, I can do a double angle identity to evaluate. But now, if I want to find half of it, now I can do a half-angle identity. Now I will say, half-angle identities are not going to be used a ton, just because a lot of those values we can evaluate using either double angle or sum of difference identities. So we typically will only do sum of difference and double angle. We're not going to do half angles very often, just because sum of difference and double angle pretty much take all those values. So it's just another way of evaluating. So we're just going to start off by evaluating certain values using half-angle identities. So first off, I have cosine of 15 degrees. So I know that this is the same as writing cosine of 30 divided by 2, which means my angle in question that I'm going to reference is going to be 30 degrees. So over here, I'm actually going to use an angle of 30 degrees for when I plug into my half-angle identity. So what's going to happen is for cosine, so for the half angle, I want to evaluate 30 degrees divided by 2. I want to do the half angle. So my angle here is going to be 1 plus cosine x, and then divided by 2. So I know those square roots can make these a little bit more daunting, but it's just algebra. So you're going to plug in that 30 for your x value. So now we're going to have 1 plus cosine of 30 degrees, and then we're going to divide it by 2, and then we're going to simplify this. So when I plug in, so we're going to have 1 plus cosine of 30, which is going to be root 3 over 2. And then that's all over 2. Then I'm going to draw my radical. Now what I'm going to do here is I'm going to go ahead and get a common denominator so I can start consolidating the numerator. So this is going to turn into 2 over 2 plus root 3 over 2, and that's all divided by 2. And then what's going to happen now that I have a common denominator, now I can go ahead and rewrite the numerator as 2 plus root 3, and then that's going to be all over 2, and then divided by 2. Now I'm taking this step by step, so when you get more comfortable with these, you can start doing a couple steps in one. So the next part I'm going to do is now I'm going to rewrite, and I'm going to move that 2 right here. I'm going to move this to the bottom. So what that's going to look like is now I'm going to have 2 plus root 3 over 2 times 2, and then that's all under the radical. So this is going to be, go away, 2 plus root 3 all over 4, and then I'm taking the square root of all this, and then the next thing I'm going to do is I'm going to split that radical. So I'm going to do a radical of the top. So I'm going to do 2 square root of 2 plus root 3 all over the square root of 4, because we can evaluate square root of 4. Plus, we can't have a radical in the bottom. Go away. Plus, we can't have a radical in the denominator, so technically we need to rationalize, but we can evaluate the square root of 4, so technically we don't have to rationalize in this case. So this would be the square root of 2 plus the square root of 3, and then that's going to be all over 2. So this is your simplified version of evaluating. Now, of course, I can also evaluate this using a sum and difference formula. So I could even do cosine of 45 minus 30 and evaluate it and get the same thing. Now, the answer would look different. Go away. The answer would look different and be in a different form, but mathematically, it's the same value. All right, now I'm going to go ahead and move on to number 12. So we did a degree problem in the previous one. Now we're going to move on and do a radian. So same idea with this one. This is going to be the same as doing sine of a radian divided by 2. So you're essentially going to take this radian value that you have here and you're going to multiply it by 2. So pi over 8 times 2 is going to give you 2 pi over 8, which is just pi over 4. So that's how you can evaluate the value that we're going to have in the numerator. So we're evaluating sine of pi over 4 divided by 2. Which means the x value in question that we're going to plug in is going to be pi over 4. So that's really the only thing that's going to be a big change on this is we can go back and forth between the radians and degrees. So evaluating sine of pi over 8, or you can write pi over 4 divided by 2, it's up to you. It's really all the same. So this is going to be the square root of 1 minus cosine of x, all divided by 2. So I really should have plugged in for my x value, but we'll do that next. So 1 minus cosine pi over 4, and then all divided by 2. So as you can see, these are some real fun problems with those radicals. So now I'm going to plug in and actually start simplifying, or rewriting rather. So this would be 1 minus root 2 over 2, and then that's going to be all divided by 2. So then I'm going to change this to 2 over 2 minus root 2 over 2, get a common denominator so I can combine. And then when I get here, I'm going to have 2 minus root 2 over 2, and then all divided by 2 when I consolidate the numerator. And then I'm going to rewrite as 2 minus root 2 all over 4 when you move this 2 right here when you move this to the bottom. So now I'm going to separate. So I'm going to have the square root of 2 minus root 2, and then that's going to be over the square root of 4, which when I simplify, so now we're going to have the square root of 2 minus root 2 over 2. So that would be your simplified form. Gross. Now for tangent down here, so I'll also do tangent. I just realized those are both pi over 8. Let's actually change u. I believe I changed this in the new copy, but I guess it didn't come over. So I'm going to change this one to 5 pi over 12. I'm going to wing it. We're going to see how this goes. Hopefully it's not a complete and utter disaster. Alrighty. So for tangent, with these, so first I want to evaluate what my x value is going to be. So I'm going to multiply this by 2, which means I'm looking at 10 pi over 12, which is going to be 5 pi over 6. So I'm doing a half angle of 5 pi over 6. So what this means, we have 2 options for tangent. So before I do those options, let me actually write the coordinate for 5 pi over 6, which is going to be negative root 3 over 2, comma positive 1/2. And I'm going to do that on purpose, because if you look at the identity, the half angle identity for tangent, we have 2 options. You can do sine over 1 plus cosine x or 1 minus cosine x over sine x. So what I do, so we have sine x, 1 minus cosine x, or we could do 1 plus cosine x over sine x. Now the reason I'm writing both of these, hold on, those are backwards. 1 plus in the bottom, 1 minus in the top. So the reason I do this is because notice how over here your x value, which means your cosine value, is going to have a radical. So I want to avoid putting the radical in the denominator so I don't have to rationalize. So which means I want to do the identity where my cosine is going to be in the numerator. So that tells me that doing 1 minus cosine x over sine x, this one would be ideal. You can do sine x over 1 plus cosine x, but the math would be way more intensive. So I'm going to stick to doing 1 minus cosine x over sine x. So I'm doing tangent of 5 pi over 12. So when I plug in, so now I'm going to do 1 minus cosine, and I'm going to do cosine of 5 pi over 6 over sine of 5 pi over 6. So when I plug in, so 1 minus cosine is going to be negative root 3 over 2, and then that's going to be all over 1/2. So I'm going to go ahead and multiply by the reciprocal since I'm dividing by a fraction. So I'm going to multiply by 2 over 1 times 1 plus root 3 over 2. So then this is just 2 times 1 plus root 3 over 2, which means your value here is going to be 2 plus root 3, which that should look familiar from when we do sum and difference identities. And as you can see, this was way quicker, and personally I think way easier than doing a sum and difference identity for tangent. So I think the half angle identities for tangent are actually way more manageable than the sum and difference, but that's just me. So that was just evaluating given a specific degree. Now we're going to find all the half angle values given the following measurements. So up here we're working with some sort of angle. Now down here we're going to be working with measurements of a triangle. So with this problem here, so we give you that sine of x is equal to 3/5, where it's between 0 and pi over 2. Now if I'm between 0 and pi over 2, that should be your indicator that we're going to be in quadrant 1. So as kind of a quick little recap, I say quick very loosely. So we have 0, pi over 2, pi, 3 pi over 2, and then all the way back around to 2 pi. So if you're ever 0 to pi over 2, then we're going to be working in quadrant 1. If you are ever going to be between pi over 2 and pi, then that means you're working in quadrant 2. And then if you're ever going to be between pi and 3 pi over 2, that means you're going to be working in quadrant 3. And if you are going to be between 3 pi over 2 and 2 pi, that means you are going to be working in quadrant 4. So keep that in mind. So here's a good little graphic for you to kind of keep in mind. Go over there. So one important note that I failed to mention, so that's kind of my fault. So I'm going to write the identities up here, which I said I was going to do and I didn't. Shame on me. So I know sine of x over 2 is going to be equal to plus or minus 1 minus cosine of x, and that's going to be divided by 2. And I'm going to explain that plus and minus in a second, don't worry. And then cosine of x divided by 2 is equal to plus or minus 1 plus cosine of x divided by 2. And then tangent for half angle is going to be either sine of x over 1 plus cosine x, or 1 minus cosine x divided by sine x. So you have options for those. Now, little backtrack over here. Now you see this plus and minus. I don't know what I'm doing. Now this plus and minus refers to the quadrant you're working in. So for sine, you're going to be positive if you're in quadrant 1 or quadrant 2, because that's where sine is positive. Now it's going to be negative if you're working in quadrant 3 or quadrant 4. So you just need to know when to add that negative if you need it. And then same idea over here for cosine. So we're going to be positive if we're in quadrant 1 or quadrant 4, and then negative if quadrant 2 or quadrant 3. And then with tangent, notice how there's no plus and minus. That's because the sine of the angle will be taken care of when you actually plug in for sine and cosine. So you don't have to add in that positive or negative. It'll be taken care of for you when you actually evaluate. So luckily enough for us, we didn't have to worry about needing to worry about the plus or minus in these 3 problems up here that we did for the half angles, but that is going to be important for when we come down here. Okay, now to resume. So I know I'm going to be working in quadrant 1, so I'm going to give myself a cute little graphic. So I'm just going to draw quadrant 1. I'm not going to worry about the other 3 quadrants. So I'm going to draw a triangle. I'm going to triangulate. So here's my fancy handy dandy little triangle. So my degree value is x, which is going to be from your actual problem here. And then we're given sine is equal to 3 over 5. Now I know this is going to be the opposite over the hypotenuse for your trig ratios. So I know opposite will give me 3, and then the hypotenuse will give me 5. And then you can do Pythagorean theorem to find your missing leg. Or if you know it's a Pythagorean, how rude. Or if you know that it's going to be a Pythagorean triple, then you can just write it in. So when you get here, in order to evaluate your half angle identities, you do need to know what your sine, cosine, and tangent values are. You don't really need to know tangent, but you do need to know sine and cosine for sure. I just like to evaluate all three just for habits. So sine of x is going to be the opposite over the hypotenuse, which is 3/5. Cosine is going to be the adjacent, which is 4 over the hypotenuse, which is 5. Tangent is going to be your opposite over your adjacent, which is 3/4. So now that we have our sine and cosine values and tangent, now we can evaluate the half angles. So I'm going to do sine of x over 2 first. So I write the formulas every time I use them just because it helps me remember them. So sine is going to be 1 minus cosine x, and that's going to be over 2. And now I'm going to plug in. So we're in quadrant 1, so I don't have to worry about adding a negative. So 1 minus cosine of x, which in this case, I'm going to plug in that 4/5. So minus 4/5, and then that's going to be all divided by 2. And then all of this is in the radical. So I'm going to rewrite the numerator. Go ahead and just get a common denominator. So that's going to be 5 over 5 minus 4 over 5, which is going to give me just 1/5. So this is going to be just 1/5, all divided by 2, which now I'm going to move it to simplify. So I'm going to have 1 over 2 times 5, which is going to be the square root of 1/10. So then I'm going to separate the radical. So we have the square root of 1 over the square root of 10. So we have 1 over the square root of 10, but now we have to rationalize. So I'm going to multiply by root 10 over root 10, which is my funky form of 1, which is going to give me my root 10 over 10. So that would be your half angle value for sine. Now we're going to do the half angle for cosine. So half angle for cosine, so we're going to have 1 plus cosine x, and then this is going to be divided by 2. So as you can see, the identities are very similar. So now we're going to have 1 plus 4/5. So since we already did something very similar, I'm going to try to skip a few steps. So 1 plus 4/5. So what's going to happen here? So we're going to have 5 over 5 plus 4/5, which is going to give you 9/5. So that's going to be 9/5, all divided by 2, which is going to give you the square root of 9 over 10. So square root of 9 is going to give me 3 over the square root of 10. Then we're going to rationalize, which is going to give me 3 root 10 over 10. So that would be your half angle value for cosine. Now we're going to do tangent. So for tangent, it's not going to matter which of the following forms or variations you do. So I'll do 1 minus cosine x over sine x. So 1 minus cosine x, so cosine, which is 4/5. And then that's going to be over sine, which is 3/5. That's a terrible 3, but you get the idea. So 1 minus 4/5, as we know, is going to be 1/5 over 3/5. So when you divide by a fraction, I'm going to multiply by the reciprocal. So multiply by 5/3, which is just going to give you 1/3. So here are your 3 half angle values, which is what we're looking for. Ta-da! So 16 is very similar, so I'm going to skip 16. Just know that that's going to be in quadrant 3. And then for 17, we're going to do this one, because this one's a little ugly. Oof. She's not very friendly. But brace yourself. So over here, now we're going to have cosecant of x equals 3, where it's between pi over 2 and pi. So between pi over 2 and pi, that tells us that we're going to be working in quadrant 2. Now in quadrant 2, keep in mind your cosine value is negative. So I'm going to draw a quadrant 2 figure. And then I'm going to draw my fancy little triangle. Woo. So my x value here, now we need to fill in the given information. Now, if I'm given cosecant of x is equal to 3, this is going to be the same as 3 over 1, and then with cosecant, it's the reciprocal of sine. So instead of doing opposite over hypotenuse, now we're going to do the hypotenuse over the opposite. So that tells me that my hypotenuse is going to be 3, and then opposite is going to be 1. So now I need to know what my last leg is down here. So I can do Pythagorean theorem. So I'll just do it really quick over here. So I know a squared plus b squared is equal to c squared. So 1 squared plus b squared is equal to 3 squared. So b is going to be equal to the square root of 9 minus 1, which means b is going to be equal to the square root of 8, which when you simplify that radical, that's going to be the same as 2 root 2. Excuse me. So for this x value here, yes, I know it's going to be 2 root 2, but what you need to remember is that we're working in quadrant 2. Quadrant 2 is negative. So we have to make sure that we remember to include that negative. So now that I have all the sides of my triangle, now I'm ready to actually fill in the ratios. So sine of x is going to be 1 over 3. And then cosine of x is going to be negative 2 root 2 over 3. Oh joy, that'll be fun to work with. And then tangent of x is going to be 1 over, or negative 1 rather, over 2 root 2, which when you rationalize, it's going to give you negative root 2 over 4, which, I mean, we don't even need the tangent value, to be honest. All right, now for the fun part. So now we're going to evaluate the half angles for these specific angles. So sine is positive in quadrant 2, so I don't need to add a negative. So I'm going to do 1 minus cosine of the x value, and then that's going to be over 2. So when I evaluate, yeah, y'all brace yourself. This math is about to get real ugly. So I'm going to subtract the cosine value, so minus negative 2 root 2 over 3 all over 2. So this is going to turn into a hot mess, but it's going to turn into, I'm going to go ahead and get a common denominator, 3 over 3. And then minus negative is going to turn into addition. So 2 root 2 over 3. I cannot draw. Over 2. And then I'm going to go ahead and consolidate the numerator. So this is going to be 3 plus 2 root 2 over 3, and then all over 2, and then that's all in a radical. Now I'm going to move this 3 here to the bottom, just like we did before. So I'm going to start it over here, but then I'm going to move it. So this is going to be 3 plus 2 root 2 over 6, and then that's all in the radical. Come here. Now what I'm going to do is I'm going to separate, because we technically have square root of 6 in the denominator, so we're going to have to rationalize, which rationalizing this thing is going to be annoying. So in the numerator, we're going to have square root of 3 plus 2 root 2, and then we're going to be over the square root of 6. Now when you rationalize, I'm going to rationalize based on the value in the bottom. So this is going to give me root 6 times root 6, or not, root 6 over root 6 to rationalize. Now keep in mind, I'm going to kind of pause here for a second. Actually, no, I'm not. Scratch that. I'm going to pause in the next step. So I'm going to do root 6 times the square root of 3 plus 2 root 2, and that's going to be all over 6. Now I'm going to pause. So what I want you to kind of look at is notice how we have square roots here and here. If I do a square root of x, that's the same as, nope. If I do the square root of x, that's going to be the same as doing x to a 1/2 power. Now, these all are going to have the same exponent, which means I can technically combine these into one radical. So how I'm going to rewrite this is I'm going to do square root of 6 times 3 plus 2 root 2. And that's going to be all over 6. And then I can simplify this beast. So this is going to be equivalent after I distribute. So now I'm going to rewrite it as 18 plus 12 root 2 over 6. And this is the final that we want. And that's just for sine. We still got cosine and tangent to do. Oh, goody. All right, so now I'm going to go ahead and do cosine of x over 2. I'm going to try to do this one a little bit quicker since we just did sine. It'll be the same mechanics. So 1 plus cosine of x divided by 2. Now, in quadrant 2, cosine's a negative, so I do have to add in that negative. So we're going to have 1 plus cosine, which is going to be negative 2 root 2 divided by 3. And then that's going to be all divided by 2. This looks fun. So this is going to be a negative. And I'm going to go ahead and rewrite it at the common denominator. So 3 over 3 minus 2 root 2 over 3. And then that's going to be over 2. And then with the negative. So I'm going to go ahead and consolidate the numerator. And then I'm going to go ahead and move the 3 to the bottom. So this is going to be 3 minus 2 root 2 over 6. So I did 2 steps in one here. And then I need to go ahead and rationalize. So I'm going to separate and then rationalize. So I'm going to have the negative square root 3 minus 2 root 2 over the square root of 6. Then when I rationalize, I'm going to multiply by root 6 over root 6. So when you get here, whoops, don't forget your negative, as I almost did. So then I'm going to go ahead and combine these into a single radical. So this will be 6 parentheses 3 minus 2 root 2 over 6. And then I'm going to go ahead and distribute after I fix this radical. So then this is going to give me a negative square root of 18 minus 12 root 2 over 6. No, my negative. There we go. So there is the half angle for sine and cosine. Now I need to do tangent, but tangent won't be as bad. So with tangent, you want to look at your values, see which ones have the radicals between sine and cosine. So cosine has the radical here, which means I want to do the variation that has cosine in the bottom. Wait, no I don't. I want sine to be in the bottom. Sine doesn't have a radical. I don't want to rationalize. So I want to do 1 minus cosine over sine x. Okay, so tangent x over 2. And because I have the memory of a goldfish, I already forgot which one I'm doing. 1 minus cosine x over sine x. Ta-da. All right, now I'm going to move this down a bit. Ooh, y'all, this video is long, but it's okay. So 1 minus cosine x, so cosine x, which is the abysmal negative 2 root 2 over 3. This problem is so disrespectful. Over sine of x, which is going to be 1/3. So I'm going to go ahead and multiply by the reciprocal. So I'm going to multiply the numerator essentially by 3. Then 1 plus 2 root 2 over 3. And then distribute the 3. So this is going to be 3 plus 2 root 2. Tangent was nice. Thank you, tangent. Whew. That was a really long problem, but it was a good problem. All right, now we're going to do these problems over here. Now, this page is really kind of a recap. I know we've kind of already done some of these problems, but we're gonna just start with 20. So with number 20 here, so we have f of x equals 4 inverse sine of x over 2 root 2 plus pi over 6, and we want to find the the output value when the input is the square root of 6. So this just means that we're going to plug in the square root of 6 for the x value, and we're going to evaluate. So when we get here, so we're going to have 4 inverse sine root 6 over 2 root 2 plus pi over 6. So I'm going to simplify square root of 6 over square root of 2, which is going to turn into the square root of 3 in the numerator. So this will be 4 inverse sine of root 3 over 2 plus pi over 6. And then when you get here, I can actually evaluate inverse sine of root 3 over 2. So sine, or inverse sine rather, as a quick little recap, inverse sine only exists in quadrant 1 where it's positive, in quadrant 4 where it's negative. Now I want to evaluate it when the actual sine value is positive. So sine is positive in quadrant 1 and in quadrant 2, which means we're looking for where they overlap. So that means our radian is going to be in quadrant 1. So over here, this value right here is going to turn into a radian. So we're going to be left with 4 times where that radian is. So inverse sine of root 3 over 2, that's going to happen at pi over 3. And then plus pi over 6. So when you rewrite, so 4 pi over 3 plus pi over 6. So now we need a common denominator. So I'm going to multiply the first one, multiply the top and bottom by 2. So we're going to get 8 pi over 6 plus 1 pi over 6, which is going to give me 9 pi over 6, which is going to give me 3 pi over 2. Ta-da! 21 I'm going to come and do last because that one's absolutely disrespectful. 22. So we are going to let f of x equals inverse tangent of 3 pi x plus pi over 6, and we want to find x when f of x is equal to inverse cosine of 1. So I'm going to go ahead and just kind of format it. So I'm going to have inverse tangent of 3 pi x, and then add pi over 6. And then we're going to set that equal to inverse cosine of 1. So what we're doing is we're solving this equation for x in layman's terms. So we need to evaluate the right side. So what's going to happen is we're going to have inverse tangent of 3 pi x plus pi over 6, and then inverse cosine. Now inverse cosine, as a recap, exists only in quadrant 1 where it's positive and quadrant 2 where it's negative. But we're evaluating when cosine is positive, since it's positive 1. So cosine is positive in quadrant 1 and in quadrant 4, which means we need to work in quadrant 1. So your value where cosine is actually going to be equal to 1 is actually going to be at the radian of 0. So now we're just going to solve. So I'm going to move the pi over 6 over, so I'm going to subtract it on both sides. So this is going to turn to inverse tangent 3 pi x equals negative pi over 6. And now what I need to do is I'm going to get rid of the inverse tangent. Now when you do this, I need to take tangent of both sides. So I'm going to undo the inverse, essentially. So when we do this, then that's going to simplify on the left side to just 3 pi x. And then we want when tangent is equal to negative pi over 6. So you have options if you're not comfortable with the negative radians. You can always add 2 pi and find a coterminal angle if you're not comfortable with those negatives. So that means 3 pi x equals tangent of 11 pi over 6. So this is the same as this. So it doesn't matter how you do it. You don't have to do this step if you don't want to, but it's really up to you and your comfort. So 3 pi x is going to equal tangent of 11 pi over 6. So that's going to give you a negative root 3 over 3. And then I need to get rid of the 3 pi on the left side. So I'm going to divide or multiply rather, by 1 over 3 pi, which is the same thing. So my x value is going to be negative root 3 over 3 times 1 over 3 pi. So this is going to be a negative root 3 over 3 times 3 pi, which is going to give me negative root 3 over 9 pi. So, ta-da! So I will say 19 is pretty straightforward, just like 20. It's just another variation. 22 is, I would say, somewhat straightforward. But 21 is where I was starting to lose my marbles, because I was like, holy cow, this is annoying. So just in case 21 requires a lot of room, I'm going to shrink all that. So 21. So this one is deceivingly, I would say, it's deceivingly difficult. So you want to let f of x equals sine of 2 pi x plus 1, and you want to find the values on the interval from 0 to 2, where f of x is equal to cosine of negative pi over 3. Now, the reason I say this problem is deceivingly difficult is because we're given an interval, and we want to find all the values on this interval. Not just 1 or 2 or 3 or 4 or whatever. We want to find all possible on that given interval. So there could be a bunch, potentially. So we're going to set it up just as per usual. So sine of 2 pi x plus 1, and we're going to set that equal to inverse cosine, not inverse, hello? Well, that would be fun. So cosine of negative pi over 3. So just like before, you can find a coterminal if you're not comfortable with using negatives. So just in case, so this is going to be sine of 2 pi x plus 1, and then that is the same as doing cosine of 5 pi over 3. So in case you prefer working with just positives, there you go. So now I'm going to evaluate. So sine of 2 pi x plus 1, and that's going to give you cosine of 5 pi over 3, which is going to be equal to 1/2. So the next step is I'm going to go ahead and subtract 1 on both sides. So that's going to leave me with sine 2 pi x equal to negative 1/2. So for this next part, I'm going to ignore the b value for a second. So I'm just going to evaluate sine of x where it's equal to negative 1/2. So that's going to happen at, ooh, my brain is not working. So that's going to be 7 pi over 6 and 11 pi over 6. So what's going to happen is now I'm going to take these values and we're going to set those equal to 2 pi. Sorry, my brain's, oof, this video is long, y'all. So 2 pi, forgot my x. Don't we all? No. There we go. So 2 pi x equals 7 pi over 6, comma, 11 pi over 6, which I'm going to now multiply everything by, hello, go over there. Now I'm going to multiply everything by 1 over 2 pi, which means we're going to have x equals 7 over 12 and 11 over 12. Now, what you have to be careful about is, actually, it's very similar to the questions up here. It's because we're in that given interval. So we need to evaluate the period. So what's going to happen is we need to find the period. So the period, we're going to do 2 pi over whatever the b value is, which in this case, the b value is 2 pi, which means it's equal to 1. So I'm going to do both solutions up until we get to a value of 2. So let me kind of see what we're working up to. So if I'm going from 0 to 2 on this interval, if I have a common denominator of 12, that means I'm going to be going from 0 to 2, which is the same as doing 24 over 12. So I know I need to look for a numerator value with a cap of 24. So for the first one, I'm going to do 7 over 12. And then we're going to add the period, which is 1. Now, if I have a period of 1, I'm going to rewrite it as 12 over 12 when I add it. So plus 12 over 12, and then that's going to equal 19 over 12. And then I still want to add potentially another period because we want to find all possible within that interval. And then that's going to give me 31 over 12. So I want the original, the 7 pi over 12, not pi, 7 over 12, and I want 19 pi over 12. But the 31 pi over 12, it exceeds and it's out of the interval. So I don't want that one. So now we're going to do the other solution. So the 11 pi over, not pi, hello, 11 over 12. So once again, I'm going to add a period of 1. So that's going to give you 23 over 12, which it works. It's in the interval, but it's cutting it real close. So we are going to have these 4 values. So my solutions here, so we're going to have 7 over 12, not pi. So be very careful not to write pi. So 7 over 12, 11 over 12, 19 pi over 12, and 23 pi over 12. Not pi. So, ooh, Lord. So we only want the single interval here, so we're not going to do all possible. So just these 4. I need to go take a fat nap. Bye-bye.